3.141529265358979.
That's correct. I would get to 3.1415 and then call it quits. So it'd be like 2, 9? No, 8? And I'd lose it. Welcome to the PAM Talks. Each episode, we interview a new physics and astronomy mentor, exploring the universe through the lens of diversity. My name is E. Thompson, and I'm your host for today. I'm an undergraduate student in mathematics and physics at the University of Calgary. In celebration of Pi Day, we're deviating a bit from the norm and taking a tangent into the world of math. Joining us is Jenny Lawson, a PhD student in mathematics at the University of Calgary, and also the president of the Mathematics Graduate Student Association. Jenny did her undergraduate at the University of Guelph in mathematics and statistics before pursuing a master's in mathematical modeling related to ecological systems at the University of Calgary. Currently, Jenny is in her second year of a PhD in mathematics combined with education research. For today's special episode of the PAM Talks, we will dive into the interplay between mathematics and education and how it all connects with everyday life. This is the PAM Talks, where the universe is as diverse as the minds unraveling its mysteries. Coming up next, my interview with Jenny. Hi, Jenny. Thanks so much for joining us on the podcast today. Would you like to introduce yourself?
Yeah, thanks so much, E. Thanks for having me here. This is an amazing project. So my name is Jenny Lawson. I'm an interdisciplinary PhD student here at the University of Calgary, and I study mathematics and educational research. So what that means is that I have research in two areas. The first is in mathematics. I study mathematical biology and these things called reaction diffusion equations, and I apply these to systems of populations. And so looking at sustainability and harvesting within those populations and systems. And then on the education side of things, I broadly study mathematical modeling and what that looks like in the undergraduate curriculum.
That's really cool to hear about how you're able to combine those two very interesting and important fields together. So I was wondering, you mentioned a bit that in both of your parts of your interdisciplinary PhD, you do work with mathematical modeling. For our audience that doesn't have much of a math background, how would you describe mathematical modeling?
You're coming out with the hard questions early. So here's the problem. No one has a great definition of mathematical modeling because every person that does mathematical modeling will have a different purpose to it. So that makes the definition a tiny bit, depending on who you talk to, you could get different definitions. The definition I read this morning that I thought was maybe a decent one for today was broadly a mathematical model has two parts. One is that there's something of interest to you, so some phenomena, and there's some math that you use to study that, so some set of mathematical relationships. So there's that kind of dual aspect to it. So something of interest and then math that you can use to study that phenomena. So a lot of times that can show up as like we're trying to model things in the real world. So for me, in my research, I model biological systems and biological populations, and I look at, what does it mean to have a fishery? And how can we mathematically model those populations all interacting in that ecosystem? On the other hand, some people think that, just doing any kind of mathematics and applying different types of mathematics to different areas of math can also be mathematical modeling. It depends on what you want to describe it as, though. But mathematical modeling has a ton of uses, and mathematical models are really everywhere.
That's really cool. Yeah, it's really interesting to hear you talk about how math, which a lot of people kind of see as separate to reality, interacts with our everyday lives. Like you're mentioning fisheries and things. Do you have any insight on that gap between like people's interpretation of math being like, okay, it's just this isolated, almost philosophical field that doesn't really care about society, and then like, oh, actually, no, this, especially in your case for mathematical modeling, this like actually does a lot of things that we care about in the real world, like ecosystems, economics, and a lot of other things.
Yeah, good question. Because usually when you tell someone you're doing a PhD in math or a master's in math or an undergrad in math, their first response is, oh, I hated math in high school. Never want to see it again. And that always makes me a little bit sad, right? To think that they've had such a bad experience with math that they would never want to see it again. That's awful. Math can be beautiful and wonderful, and it can be such an exciting way to view the world. And it doesn't have to be just, finding the answer in the back of the book and being like, well, I got that wrong. But it can also just be, surprising discoveries that you come upon along the way that you're like, oh, I never would have imagined that. Or different things that, like fractals are a beautiful representation that you get by math, right? Historically, mathematics evolved out of something that we can see, right? So if you look at historical concepts of what a number is, a number was a collection of objects. And that was great. But then along the way, people kind of realized that as they started to get into more complicated problems, they needed more philosophical kind of, algebraic definitions of things. And so I actually think there's always been a relationship between the two because you can't have one without the other. Like, we never would have gotten into math without that start of being like, oh, I have 3 loaves of bread and now I have 4 loaves of bread. That's nice. But also, we would never get farther if we didn't have that kind of philosophical understanding of math and that like real pure mathematics research. So, right now, I'm TAing a course and we're learning about the history of complex numbers. And to a lot of people, complex numbers are the stupidest thing you can imagine. They're called imaginary, for heaven's sakes. Like, what the heck is that? But it's been fascinating to learn a little bit about the history behind that and how complex numbers came about because we were trying to do very practical things. We were trying to solve equations. And all of a sudden, you got to this spot where you had the square root of -1 and people went ballistic. And then some mathematicians were like, well, we're going to try using it. And then somehow magically it just worked out that they managed to solve this equation and they got real answers. There's always been that relationship between, they were trying to do this very practical thing, but they needed this really, imaginary thing, which is real. But yeah, so I think they're closer together than you might think, but they just have two different ways of coming at the problem.
That's a really beautiful perspective to have on both the history of math as well as the connections between it and society. So, kind of going back to what you were mentioning in your introduction, you mentioned that you did your master's just in modeling. So, what kind of spurred on this desire to actually mix it with education as well, rather than just continuing modeling through your PhD?
So that's a kind of an interesting story. I did my master's looking at delayed impulsive harvesting equations and looking at maximum sustainable yields, which has applications to fishery science. And what I kind of stumbled across in the process of doing this kind of research was the history behind it and the history behind the maximum sustainable yield specifically. And the story basically goes that kind of in the 50s, the later 20th century, mathematicians came up with this concept of the maximum sustainable yield. And what they were able to do is they were able to use differential equations. So, complicated equations with derivatives in them. They were able to use those to model how a population reproduces. The maximum amount that you can take out while still ensuring sustainability is this number. So that was great. The problem was people took it and they ran with it and bad things happened. So the famous example in Canada, at least, was the collapse of the cod fisheries on the Grand Banks of Newfoundland in the 1990s, right? There was just so much overfishing that these populations could not survive anymore and the catches were dwindling and dwindling. And there are many reasons for that, but some of the reasons why people think this happened was people took ideas like the maximum sustainable yield. So they took quotas for what they could catch and they said, oh, I'm just going to go a little bit more, right? Like, it's more of a target to be aimed at than like an absolute limit, like do not go past this point. And so what they didn't realize was that if you go past the maximum sustainable yield, it's not sustainable anymore and you will end up sending your populations to extinction. And so I was fascinated by the fact that I was using this concept, the maximum sustainable yield, and it still had all this baggage and history behind it. And I was curious about how one would take my research, but then still manage to get it into policy in a way that wasn't going to be harmful. So yeah, that was kind of the question that I had. I was like, well, how do I keep studying this when I know all the history behind it? And then I thought, well, the the math wasn't wrong. If it was, that would be bad. So what else is going on here? And then I kind of had this idea where I was like, well, it's all about how we use these models and how we interpret our results from these models, right? So I thought, well, how are we teaching students to interpret these models? And that question really spurred on this additional interest in education. And that's where I ended up, was because of this question. Like, how do we actually teach students to interpret mathematical models? That's a pretty important question.
I'm glad that you're researching that, and it makes me hopeful that things get a little bit better in the future so that we don't have incidents like that happening on a regular basis. So now kind of going back a step. So we talked about why you went from your undergrad into mathematical modeling and master's, but what from before undergrad, what made you want to go into math?
Yeah. So I actually didn't start my undergrad degree in math. I started in biomedical engineering, and it took me 6 weeks to realize that was a terrible, terrible decision. Um, so I made it to 6 weeks and I was like, no, this is not for me. And I had to figure out what I was going to do next. And it turned out that I had a calculus class and prof that was also a woman, and she was basically like an older Jenny. And so she looked like me, she talked like me, and it was probably the first time that I ever realized that you could do math and not be an antisocial nerd. So, because like growing up, I always knew that I liked math, right? And I remember coming to the end of high school and being like, man, I'm really sad I'm not going to be able to do math anymore. But I never thought that that was going to be something that I could do. That was only for geniuses, right? To go and do a math degree, that's crazy. But it was really seeing another person doing math that looked like me and that talked like me. And I was like, oh, actually, I think I can do this now. And so I just decided to give it a shot. I switched into the mathematical science degree at the University of Guelph, and I really enjoyed it. We got to study some really cool things, do partial differential equations. We also got to have an area of emphasis. So I got to do some work in computer science as well. And yeah, that kind of spurred everything on. I actually ended up getting to do research with that prof that inspired me to get into math later on, and we're still good friends.
So cool to see how concrete representation can be as a force for driving people to pursue what they enjoy. I guess as a final question, do you have any kind of pointers or notes for other people that are thinking about going into either maybe a math or STEM type field, but aren't sure, like how you said originally, it's like, oh, this might be restricted for this class of geniuses or something. What would you say to someone like that who's thinking about it but is hesitant?
Don't be afraid. There is so much that I was afraid to do for so long until I, worked up the courage and got in there and found out that I was actually good at it. So I'll tell you a story about my undergrad. I took a computer science class in my first year of my undergrad in the first semester, and I had never coded before. So this was like totally new to me. I thought it was really cool, but I got back my third assignment and I had got a 38% or something like that. And that I think was the first time I had ever failed something in my life. And I was like, well, that's so much for that. I guess I'm just not good at this. And I carried with me that feeling or that thought of like, oh, I'm just not good at coding. I just can't do coding. And I would like, choose courses based on the fact that there was no coding in that course until I got into an upper year in I think second year, and I had to take a math class that had coding in it. And I was terrified, but I had to take it to get to my degree. So I was like, I guess I'm doing this. And I can remember going into the computer lab for the first day, and I was physically shaking. And I was like, this is the worst. I tried to sit down at a computer. I was so nervous. I couldn't figure out how to turn the computer on. I went to 3 different computers until I figured it out. But once I got into it and got started, I was fine. I actually enjoyed it. And I was like, maybe I can do this. But it really took that moment of just, overcoming that fear and getting into it and like, no, I can actually do this. One failure doesn't mean that you're a failure, right? And I think that's something that I wish I would have known before.
It's a really nice story. And also I feel like a very good point that it's hard to, after one mess up or one setback, to think it's like, okay, that's it. It's over. Call it quits. That's amazing. Thank you so much for, again, coming to talk with us today on the podcast, Jenny.
Well, thanks so much. This is great.
Well, that's the end of this episode of the PAM Talks. Thanks so much to Jenny Lawson for joining us. Stay tuned for our next episode, where Gabby Gellinis will interview Paula Brandt, a PhD student in medical sciences at the University of Calgary. Get ready to explore the universe through the lens of diversity, and join us in celebrating the brilliant minds breaking barriers in physics and astronomy. The PAM Talks gratefully acknowledges the support from the University of Calgary Graduate Students Association Quality Money Grant Program.